Okay, thanks, Marco. All right, so thanks for the introduction. So in this talk, what I want to do is basically to show you what I've been recently involved in about structural glasses. So for this, I would first need to actually introduce the mean field theory we have when you send the spatial dimensionality to infinity, and then so that I can actually talk about how we can solve the dynamics, classical dynamics in this limit, and apply it to some out of equilibrium processes. And in a second part, I will talk more about what happens at extremely low temperature, so where you have quantum effects that become important, and how we can capture them in mean field. And well, in the last part, I would like to mention a few possible projects I would like to do in the following years. So they are not obviously exclusive, but just to get an idea of what I'm also currently doing and what are the perspectives. All right, so let me start first by introducing this mean field theory. Well, maybe the first I would like to maybe recall what is, I think, the most striking feature about glasses. So this is basically entropy versus temperature. So maybe the most striking feature is that when you form a glass, what you do is that you typically perform an experiment in which you fix a certain cooling rate. So you start from a high temperature liquid here, and you start cooling down the liquid, and obviously at some point you will encounter this first order transition to the crystal phase. But there are basically we can tune the protocol, or you can go fast enough, perform a fast enough quench to avoid this transition, and then you will stay in this equilibrium line. Well, as you stay in this equilibrium line and you start cooling again, you will see that the relaxation time of the system here will grow by several orders of magnitude. So you can measure it either through the mean square displacement of your particles, or through measuring the viscosity that is basically proportional to it. So this means that basically when you are lowering the temperature, the viscosity becomes also enormous, and your liquid becomes more or less rigid. So that's the glassy state that is coming. And at some point, the relaxation time is so large that whatever the cooling rate that you have imposed in the beginning, your system will not follow, will not be able to relax anymore, and you will fall into one of these out of equilibrium branches that we call a glassy state. Okay, and they are basically protocol dependent, and there are a big wealth of out of equilibrium phenomena that arise there that are interesting. So let me mention that now from the theoretical point of view, well, the problem we have in such kind of system is that we don't have an explicitly small parameter like you would have, like the density in a gas, for example. And we don't have a lattice that we can start from, so like in a crystal, or, well, in other words, we don't have a reference configuration or an obvious symmetry breaking mechanism to build a theory. So the strategy that has been used in the last decade basically was to go to the large dimensional limit and use 1/d as a small parameter. And what simplifies in this limit is that, well, geometrically, if you have a particle that is short range interacting with some neighbors, basically all of the neighbors become independent, because basically it's very unlikely that you have configurations where 3 particles interact. The overwhelming majority are independent. So that's the main ingredient. You can use central limit theorem and things like that. So I'll come back to this point. And let me just now briefly sketch what happens. So in the phase diagram. So before I was talking about lowering the temperature. You could do the same by actually increasing the density. So this is this phi parameter. It's the packing fraction. It's basically proportional to the density. And so at low density, what you have here is you have a liquid state that is ergodic. The phase space is totally ergodic. And your system is diffusive at large times. But then you encounter a sharp dynamical transition here, where what happens is that the phase space splits in many basins. So each basin basically contains a lot of configurations, and you are basically trapped in this pool of configuration. You cannot escape from that basin. So in a more energy landscape picture here, maybe this means that you are in this basin and there are infinite barriers between the next one. Well, and what happens is that if you now start compressing again the system, each of these clusters will have a secondary transition, which is called the Gardner transition here, and where your cluster becomes, your energy landscape becomes marginal. So this means that you have, okay, it's a very complicated phase in where basically you have a wealth, various sizes of energy barriers. You have a lot of soft modes in the system, so flat directions in the landscape. And well, in the landscape picture, this means that basically the bottom of these clusters splits in many basins and barriers. And you can, well, actually you can push this game onto the endpoint, which basically is called the jamming point, so where you have the maximum density, where your spheres are in contact. Okay, and this, what happens basically is that the size, so if you are still in this marginal phase, and basically what happens is that the size of the smallest cluster goes to 0, and you just, this means that in the bottom of the landscape you just pick basically one configuration of your system, which is the one in which all particles are in contact and which are dependent on the way you've reached this minimum. All right, so this is called the jamming point. I will go back a bit to this transition later. So let me now go to the first part. So the first part will be about solving the dynamics of such systems. So just to compute the time dependence of the observables. So this has been done at equilibrium in those papers here, and more recently for out of equilibrium protocols. But just to make things clear, I will just choose one simple protocol. We can do more complicated, but just to fix ideas. So say, for example, you start at 0 time at equilibrium, so you pick a configuration at equilibrium from the Boltzmann distribution at temperature T0. Okay, and then you could do a lot of things, but for example, if you run the dynamics after at the same temperature, you would be basically at equilibrium all the time. Or you can do a quench, so this is non-equilibrium at a lower temperature, for example, or you can even more directly go off equilibrium by driving the system. So here, for example, we will drive the system through a shear. So shear is basically that we will strain along the direction 1 the system. So you apply a force and you apply a displacement in the direction 1. And this can be taken into account in the equations. So basically the dynamics would be Langevin or Brownian-like as you want. And you will have a dissipation term that is related to a thermonoise term at temperature T. And if you have a shear, you would have some sort of velocity flow in the dissipation term, so which is proportional to the shear rate, and which is, so this is the vector along direction 1, so which is along the direction where you strain. And well, the most complicated things I think actually here in the process are obviously the interactions, so with a potential V, interactions between your particles. All right. So let me mention what are the ingredients. Why can we solve this problem? So there are many ways to derive the equations, path integrals, cavity method, but basically there are two main ingredients. One is that since you are in the large dimensional limits, you have many directions to explore. And this means that basically the displacements of your particles are very small. They are typically fluctuating of order 1/d, and this means you can treat them as a perturbation in the equations. Then the other ingredient is that, well, in the large dimensional limits, you have order d many neighbors typically, so a very large number of them. And as I said in the introduction, they are basically uncorrelated. So you can use central limit theorem. You can simplify the dynamics with that. So what this means is that basically, if you consider a particle, all the surrounding particles will have forces on it, which will be then it will feel a large sum of forces, which basically will be a random noise, much simpler to treat, and which has to be determined self-consistently from the dynamics. And well, it's a mean field system in the end, so what happens is that the whole dynamics is controlled by actually a single degree of freedom, which is basically the gap between two neighbors, two interacting particles. So if you look at the distance between particle 1 and 2 here, the typical distance would be basically the one it has at time 0, plus a very small 1 over d fluctuation that is controlled by this h of t variable. So this is the degree of freedom, the gap that controls the whole dynamics. And basically in the large dimensional limit, what happens is that you can rescale all the parameters of the problem, so you will see bars and hats everywhere. And the equation, so let me just go through it quickly. So you will have, as I said, hats everywhere. It's just a rescaling with a dimension. And so here I write basically the dynamical equations at equilibrium. So I take the same temperature and no shearing of the liquid. But it's just to get an idea. Actually, out of equilibrium, you have a bit more complicated, but it's the same structure, basically. So what you get is that it's an effective process for this gap variable, which evolves with basically some kind of effective potential that contains the initial potential between the particles. And above all, you have these extra terms here. So it's a retarded friction term. And also you have colored noise with some kernel, memory kernel MC here. And physically what this is, it's exactly those forces on the particle that acts as a random noise on your interacting particles. So it's a picture that we like usually is that so there is no quench disorder in this system, there are just interactions. But basically the system is able to generate its own disorder through the interactions. All right, in this equation, you know everything except this memory kernel. And this memory kernel is actually computed, so it's proportional to the density. And it's basically a force, so V prime correlation function that has to be computed on this process. Okay, so this means you have this self-consistent structure between the memory kernel and the dynamics of the gap. So you have to solve them in a coupled manner, and once you have this kernel, you can compute basically every time-dependent observable you want. So here, for example, I show the mean square displacement that is expressed through this formula. So I just want to mention a few applications of it. What we did actually a few years ago is to solve in some regime analytically, to focus on some regime analytically from this equation. But I will also show numerics from that. Oops. All right, so let me first say at equilibrium, analytically, what you can show is that maybe the biggest outcome is that, well, if you increase the density, you get this sharp dynamical transition between a liquid and a glass state where you are trapped in. And what this means is that, so there is a postdoc actually at École Normale, Alessandro Manacorda, who is solving numerically the equation. So I can show you some plots so to show you what this means. Basically, if you consider a potential that is a soft harmonic sphere potential, so this means a harmonic repulsion between the spheres that overlap, and if they don't overlap, they don't interact. You can compute that this dynamical transition happens at a density which is 7.2. So basically what this means is that below this density 7.2, the mean square displacement would be at large times diffusive. But as you increase the density here, you will see that it takes more and more time to reach the diffusive system, so the relaxation becomes slower and slower. And actually, at some point, it will be even totally stopped. You will have no diffusion at the value of the transition. And so what this means is that if you initialize your dynamics in a density that is higher than this transition, then you would be trapped in a state, and this means that basically you do not relax. You will stay in a plateau value forever at large times. All right, and let me mention, just because I wanted to talk about of equilibrium, so let me go back to the setting we had before with the shear. So let's consider the following protocol. So you take hard spheres. Basically, hard spheres are spheres that interact infinitely repulsively when they if they overlap, and they do not interact otherwise. So you would start first in a glassy state at some density phi naught, so above the dynamical transition, so you are trapped in this state. Then you would compress the system at the target density phi. And once you've done that, you shear your system, and you call the final strain gamma at large times. Okay, so you can actually write the dynamical equations for it and look for the steady state, the stationary state value of observables. So this has been done in this reference, but here I'm cheating a little bit. I'm showing you this plot that is from those references actually, where at large times basically you can also develop some kind of pseudo-equilibrium approach, and you can also get the results. But just to say that, well, with the dynamical approach you can go beyond this kind of equilibrium results. But anyway, just to show you this result here, you plot the stress versus the strain. So this is the strain that you impose in the end, and the stress is basically the force that is resulting on the material. And for several value of this target compression phi, so what you have is that at small strain you have a linear behavior. So this is an elastic behavior. This is basically Hooke's law. Okay, so this is expected, but then you have two typical different behaviors if you increase the strain. So at low density, you have those curves here, and when you strain too much, at some point you will see that the stress shoots up and then goes down rapidly before you actually lose the solution at the end point. So what this means is that you have taken your system, you have strained too much the material, and at some point it just breaks due to the strain, and this is called yielding. So this typical curve like that with an overshoot is seen in experiments and simulations. And well, on the contrary, if you go to larger densities, actually, instead what you have is that the stress shoots up to infinity. So if you compute the pressure, it would also shoot up to infinity, or the mean square displacement would become 0, and this means that all your particles are in contact, and you go to a jammed state from a non-equilibrium protocol. So okay, it's a nice application of it, and you can basically describe those two kind of transitions. All right, that's all for the dynamics. I will jump to the second part. So this is about this recent paper we have here. So about the thermodynamics at very low temperature in those systems. So let me first describe the type of experimental result we want to address. So typically now we are considering a liquid or more a glass at extremely low temperature, so below 10 Kelvin. Okay, so here the glass is totally frozen. It's totally an amorphous solid. And typically what you measure in this regime is, for example, the specific heat that is here rescaled by the temperature to the cube. So say you would do that for a piece of crystal, so that's the green curve here. Well, you would recover the fact that the specific heat goes like T cube at small temperature. So this is the celebrated Debye behavior that derives from acoustic phonons. And instead, if you perform the same kind of experiment on a glassy material, you get typically two types of behavior. One is, again, a T cube law for basically glasses that are very stable, so glasses that you have prepared through a very low annealing, typically, so you have cooled them very slowly. And they are very stable, and they have this T cube law, but you see that it's quite, in large excess with respect to the one that you would expect in a crystal state. And what you can get is instead for a more conventional glass, so those are those curves, that typically you would perform a very fast quench. So it's not so stable, but what you get instead is that the specific heat goes linearly with temperature, so that's the relation here. And well, this, I mean, 50 years ago when it was done in experiments, it came as a big surprise that it would be so different from ordered solids. So, well, what you would like to do maybe to address this in a mean field manner as in the first part is that, well, you would take the same system of particles. You could take the large dimensional limit and see what happens, but here you have to include quantum effects, all right? Or otherwise you don't see any behavior, any possible behavior like that. So actually it's even a more difficult problem. So what we did instead is that we turned to a simpler model, but which is basically in the same universality class as the infinite dimensional one. So I will describe first this model.
Sorry, Thibaud,
yes.
This temperature here means the final temperature. You're cooling up to this temperature. That's what it means.
Yeah, exactly. So you perform your quench and to this temperature, and then you let it fixed.
Okay.
And then you register the points. That's what they do. And well, so basically the model we consider is very similar to the infinite dimensional one, but it's a bit simpler. It's called the spherical perceptron. So the idea is to put a particle on a sphere, which is of dimension n, and radius square root n. And this sphere interacts with obstacles on the sphere that you put at random. Okay. So in spirit, it's a bit of the same as the infinite dimensional setting, in the sense that you have a target particle that evolves in a kind of disordered background by its neighbors. In spirit, it's a bit of the same idea. And the interaction potentials between the particle and the obstacle is the same as before. So it's the potential V, which depends on basically the gap between the obstacles and the particle. So now it's a gap on the sphere, but basically it's the same. So we considered, as before, this harmonic potential. So basically when the gap is negative, so when spheres overlap, you have a quadratic cost in the potential, and if they do not overlap, they don't see each other. So there are two main parameters in this problem. One is the density, so here it would be called alpha of the obstacle. So it's the same density. And another one is this sigma parameter in the potential. So I won't talk much about it, it's not so important, it's just that glassy effects comes in only at sigma negative, but for what I'm going to say, it's not really a relevant parameter. Anyway, so the classical phase diagram, so purely classical at 0 temperature, has been computed in those references here. So it's density alpha versus this parameter sigma. And well, what you see in this phase diagram is that at low density, so this is 0 temperature. So basically the ground state at low density has no overlaps. So you have, so it's a low density phase. And if you increase the density above this red line, so which is a jamming line, the ground state would be full of overlaps. And basically this jamming line is exactly as before. It separates, I mean, it signals the point where all particles are in contact. And what happens is that this jamming critical transition has the same exponents at the infinite dimensional one. So it's the same universality class. And as in the infinite dimensional system, basically this jamming line falls into this blue region here, which is a region where the energy landscape is marginal. So it's very rugged with many valleys and many actually flat directions and soft modes. So it's a complicated landscape, and out of this blue region, the landscape is just a single basin, nothing dramatic, just a single minimum, much simpler. Okay, so what you would like to do, what you could do is, for example, if you want to compute the specific heat, is the first approximation that you can make is to consider what Debye did. So I recall you the argument. So say you are at low temperature, you are around the minimum, so you do small oscillations. Then you quantize those oscillations. And this means that every packet of energy will bring an energy h bar omega, each mode. That is then weighted by the Bose-Einstein factor. And then to get the full energy, you have to sum over the distributions of the modes. And this distribution of the modes is directly related to the spectrum of the Hessian of the system. So what is much easier in the system with respect to the infinite dimensional particle system is that this Hessian, I mean, there is a quench disorder in the system. So this Hessian is a random matrix whose spectrum actually has been computed. Actually, it's in this reference. And well, what you find is that in the single basin phase, basically in this single basin phase, the spectrum has a positive gap. So this means that you have a well-defined minimum. So it's a stable phase. And when you go into the blue region, where you have this very rugged landscape, the gaps goes to 0, and you get instead the density of state that goes like omega to the square. So here, I emphasize that due to the model, the fact that the model is on the sphere, it breaks translation invariance. I mean, everything that you get in the spectrum is on top of Debye phonons. I mean, acoustic phonons. That in this model you don't have phonons, so everything that you get is on top of phonons. In the real system, you would have the contribution from acoustic phonons as well. And then, well, inside this marginal phase, you can go to the jamming point. And if you go to the jamming point, something dramatic happens in the spectrum. You have an extensive number of soft modes, actually. So this is related to the fact that, well, all particles are in contact. So basically, each contact in the system acts as a constraint on the system. And you have as many contacts, so as many constraints as there are degree of freedoms in the system. This means that as soon as you remove a contact, you will trigger a soft mode. So you will trigger a rearrangement, a big rearrangement, essentially in the system. And okay, so this is a special point where you have many soft modes. And as a result, the density of states is much higher, it's completely flat. All right, so you see from this Debye expression that once you have this vibrational density of states, then you can compute the specific heat, and basically in the, so here we consider above the jamming line. If you have a gap, then the specific heat goes exponentially small with the gap. But then when you enter the marginal phase, it's a power law that is T cube. And when you go right at jamming, it becomes a linear specific heat, so linear in temperature. So everything is on top of the biphonons, and you have and you see that you have both this T cube and T behavior, which is quite reminiscent of experiments I showed you earlier. So that was quite exciting, but the problem is that here you have mainly two issues. The first is that, well, as I told you earlier, at jamming you have an extensive number of soft modes. So this argument of Debye that you can just perform small oscillations around the minimum, maybe that it doesn't hold because you can go far away from this minimum. The second problem is that something dramatic happens right at the jamming line. And if you include quantum effect, well, you include fluctuation in the trajectory, so you cannot define any more contact system. So basically, it's expected that the jamming transition should become a crossover if you include quantum effect. Or, I mean, in other words, the classical picture we have of jamming is you have particles at fixed position and fixed momentum, and if you had quantum effects, this cannot be. So what we did instead in this article is that we directly computed the free energy, the specific heat from the free energy of the system. So you take the same model, you have to make it quantum, so you add a momentum constraint on the sphere to the particle that doesn't commute with the position of the particle. And then you can actually write the free energy and solve the system. So basically, it's the dynamics in imaginary time, so it's a bit similar to what I showed in the first part. So it's still quite complicated. So to get the results, we had to resort to this Shear-Ledussal-Jamarki expansion, where basically you do an expansion in which you send h bar to 0 with a fixed Matsubara period. So you send both h bar and t to 0 with a fixed ratio, and I mean this gives you a mechanism to compute the specific heat at low temperature. So in which you still retain, because they have fixed Matsubara period, quantum effects. So basically the change that it brings is that so at finite h bar, what you have is that in the whole marginal phase, instead of the result I showed you earlier, you have the specific heat becomes a scaling function of the temperature over some cutoff temperature that appears, which goes in this way at low temperature. So this means that if you are at very small temperature compared to this cutoff temperature, you get a T cube low. And instead, if you are above, you get a linear low in temperature. And this cutoff temperature is basically controlled by the square root of delta, which is the distance to jamming in the phase diagram. So basically where you are according to this line. Okay, so what it means, so basically the lessons from that is that, well, if you are in this marginal landscape, you have soft glassy modes, special glassy modes in the system. This mode brings a power law contribution to the specific heat, which is in excess with respect to the crystal. And depending on this value of this cutoff temperature, you can either observe T cube or T behavior. And of course, it's more likely if you are close to the classical jamming line. So delta goes to 0, and this dramatically reduces the amplitude of this cutoff temperature. So it's kind of sort of in the quantum system a reminiscence of the fact that there is a critical transition in the classical one. But still, nevertheless, I mean, if you go really truly to 0 temperature, you never recover the T scaling. So this is related to the fact that jamming must not be there anymore, and of course it predicts the approximation close to the jamming line is totally different. All right, so that's for the second part. So now in the remaining time, I would like to address. Yeah. Yes.
The Debye expression that you have.
Yeah.
I was wondering. Yeah. So in this, somehow here you're saying that temperature enters in that kind of statistical factor, and your spectrum of modes is. So I was wondering if, in principle, if you include the quantum fluctuation, would you expect that this d of omega also would change as you change the temperature?
Yeah, no, of course, yeah.
And can you get that, or it's beyond this?
Okay. No, it's okay. So, yeah, of course. So, I mean, this is within Debye. So within Debye, it's just the class. You expand the potential, so you don't have any. The density of state doesn't change. But what we show here is that basically with the fact that that the specific heat changes, this means that the fully quantum density of states is different from the vibrational one, and that we get a mismatch between the two. Now, within this scheme, so this scheme has been mainly developed to compute the energy, the thermodynamic energy of the system. You can relate the energy to the density of states, and you can compute the density of states. Actually, we have basically the first order in this expansion of the density of states, which is actually the same as some quantum spin glasses. Then, if you want to do the fully h-bar calculation, maybe you have to address a bit the parameters. But yeah. Okay, so let me mention some projects I would like to address. So for the first two, basically, I need to introduce very quickly, so I won't say exactly what I'm doing. So with Alberto Rosso at LPTMS and Denis Basco, Marcus Holzmann in Grenoble, I just want to introduce the system. I don't have time to go much into detail, but basically what we consider is a typically condensed matter system. So you have actually that arises in nuclear magnetic resonance. So you have, for example, an organic piece of material. So you have carbons, hydrogens, and you have free electrons. I mean, free electrons in the system, and you perform a nuclear magnetic resonance experiment in order to exchange the polarization from the electrons to the nuclear spins, basically. So the important thing I want to emphasize is that, well, here in this kind of system, the electronic system is the most dominant one. And so it's a nuclear magnetic resonance, so you put a strong magnetic field, and you also irradiate your compound with microwaves. So the system of the spins are basically, so they have a Zeeman gap that is very large, but also due to the fact that they are embedded in some kind of glassy matrix, they have some disorder on some disordered field here. And of course, the electronic spins are interacting through dipolar couplings. Then on top of that, you put microwaves that drive the system out of equilibrium, and they are in contact with a bath, so typically the phonons of the system. I mean, so you have all these different pieces together that you have to treat. And basically, I want to say that, well, we know how to treat them, so the dynamics of the density matrix in a type of Lindblad master kind of equation. here, and we know how to solve this problem. And maybe I will just mention the most striking fact about this system. So in this plot here, so if you plot the nuclear polarization of the spins with respect to the strength of the dipolar interactions, so what happens in the system is that if you have strong interactions, the ensemble of the system and the macrowaves drives the system in an out of equilibrium state. And this out of equilibrium state is typically ergodic at large interactions. So basically it's described by some kind of effective Gibbs ensemble with, for example, an effective temperature associated to it. And this kind of ansatz describes very well the true dynamics of the system, also the experimental features actually. But what you see is that if you lower the interactions at some point, well, then the disorder in the system becomes dominant. And what you see is that if you would remove the bath and the microwaves, the isolated system would have a truly localized, so many-body localized transition. So the eigenstates of the system totally changes. And the result on the out of equilibrium stationary state is that it's not anymore, you cannot describe it anymore through a few parameters like a Gibbs ensemble. Okay, so once I've said that, basically there are two directions we could explore with such kind of systems. So the first one is related a bit to the fact that when we simulate this kind of equation, we have a very small number of spins. So it would be nice to actually, because I mean the Hilbert space is exponentially growing with the number of spins. So there is actually a technique that has been developed by Marco Schiro recently, where if you consider only an isolated system, you can try to diagonalize the Hamiltonian. You can try to write flow equations that make your Hamiltonian flow to an Hamiltonian that becomes easier to diagonalize. And maybe we could think of applying this kind of techniques to a more general driven-dissipative dynamics, which could be really nice to see larger systems. And the other one is basically coming back to what I showed you in the second part about low temperature glasses. So what I showed you was a mean field way to capture the behavior of the system, but actually the standard model of this is more to consider that you have a glassy matrix, which at low temperature would have some kind of defects in it. And those defects, they would act at some kind of effective two-level systems. And which have these basically disordered parameters. And basically, this model is very successful to account for some features at low temperature, but if you go around 100 millikelvin, what you see is that there are discrepancies in the model which are likely due to interactions between the two-level systems. And they arise, for example, because due to the coupling to the phonons that make an effective couplings between the spin between the two-level systems. Or, for example, in experiment, typically they probe the system through an oscillating electric field, and this makes the system makes the interactions a bit stronger. So actually, there has been this proposal of a sort of Anderson delocalization of the excitations of the two-level system that has been proposed here. And I think that with the techniques that we know now, it would be nice to revisit this kind of thing. So I'm thinking maybe to tackle this with, for example, Laura Foyni, but there is also in the next building François Ladieu that is an expert on these kind of things. To finish to this two-level system, there is also we have talked actually with Pier Francesco Urbani about how to try to bridge a bit the mean field picture with the two-level system standard model. So what the idea would be to consider, there are many things that could be done, but maybe a nice idea would be to actually use the same kind of model as before and consider to couple particles with actually a double well, like it's done in the two-level system picture, and to see what comes out in the dynamics or in the quantum regime. There has been other proposals also recently, but I mean, I won't enter into details. There are many things that can be done in this kind of systems. Maybe if I have, okay, maybe I want to mention, in case someone is interested in those themes. So I've thought about, in the last years actually, I've thought about a way to link in liquids or glasses basically classical Casimir forces to detect a kind of length scale, growing length scale in the system close to a transition. So the idea is that of classical Casimir forces is that when you have a system that is close to criticality, you expect that there's diverging length scales in the system. So typically, if in your medium you would put a wall or let's say two obstacles inside your medium, as you approach the critical transition, you expect that those, due to the medium they are embedded in, that are currently undergoing a transition, you expect that there is an effective force that they call Casimir force, like in the system, and this could be used to, to define a length scale that is growing in a more direct physical way than, well, otherwise it's quite difficult to define one actually in liquids. All right, maybe I should conclude now, or how long do I have? Yeah.
Pretty good, yeah.
Okay. No, but that's okay. I can jump to the conclusion. So, all right. So what I've tried to show here is that, okay, in the first part, I tried to show that there are many physical phenomena in transition, so both in and out of equilibrium, that you can deal with in this infinite dimensional setting. So within the same theory, basically, you can address, so I tried to show you that you can address the glassy slowdown of the relaxation, the yielding transition, also jamming. And there are still many things to do in this system that I don't have to talk about. So I will just emphasize that basically the dynamics of the system is very analogous to what you do in dynamical mean field theory of strongly correlated electrons. And well, due to new progresses, so also in simulations and in experiments in the last 15 years, now it's I think it's possible that we get a first principle theory of the low temperature quantum regime in those kind of frustrated systems. And well, about possible directions and projects, so they are either related to out of equilibrium many body quantum disordered systems, their stationary states, or higher temperature new glassy phenomena. Also, there are special types of glass-glass transition that I would like also to address, but let's stop here now. Okay, thanks for your attention.
Thank you. Questions? Christine?
Yes? Yeah, so so in the first part, basically about the dynamics. So in this kind of system, we have, actually we can write closed equations for the dynamics of the system that then you can solve numerically. Basically, so here I showed you a driven system where you basically shear a glass. So the glass could be, depending on the potential you choose, you can address the granular system, colloids, molecular glasses, a wealth of system in this way. But maybe focusing on the processes that you can address, the dynamics that you can address. So you have this kind of dynamics, but you can also do, for example, active matter, where you can tune, basically you tune, you can add a colored noise to the system that acts as basically an internal drives of bacteria or things like that make the system out of equilibrium. So we have written the equations for this active matter. You can do rheology in the system. And then, anything that breaks basically detailed balance, you could think of embedding it in these kind of equations. Yes. Yeah, so I was saying it's either related to more this kind of quantum disordered spin system, so be it two-level systems in glasses or this kind of NMR types of experiments. So then I told you about these critical Casimir things, but also actually I had another slide about this kind of glass-glass transition. So this is this is a recent article that we've made. Basically, it's more kind of numerical project, but would be that well, I showed you that you can go from liquid to glass, and basically if you tune a bit the potential in your system, so it can, that actually people in experiments in colloids, they know how to tune a bit the potential of the system. You can see that, for example, if you make the potential a bit attractive, you make a square well attraction between particles, you can have actually different types of glassy phases. So above, so here you have a re-entrance of the liquid into the glass, and basically above you have what is called the repulsive glass. So this means you are trapped by your neighbors that are repulsive, and actually below you have this kind of so-called attractive glass where the particles are trapped now because of the fact that there is this attractive sticky attraction at low distance. And what I've seen is that if you actually make a more complicated type of potential, you can have much more phases, glassy phases in the system. For example, here you have a coexistence between 5 different types of glassy phases. You can have as many as you want. So the idea would be to try to see them in a 3D type of simulation.
So you're one directly with a glassy system?
Yeah, exactly. So more classical, could be about more classical, so like dynamics of the system, glassy systems. So so obviously I've showed many papers of Pierfrancesco in the talk. So people that know well these things here. So I guess Pierfrancesco, Laura has worked a bit on it. Then I've said earlier. So Olivier Parcollet is not here, but basically the dynamical equation that I have, it's basically the MFT. So the Casimir force here, maybe. Yeah, this. This is something that we've talked already with Pierfrancesco, actually. But then, what I want to emphasize is that this is a list of things that I think could be done right now with what I know, but it's not, obviously, it's not limitative. I know the group is really big. So, for example, before my PhD, I've worked on single-phase diffusion. I know that Karen Malik has worked a lot on these things. So, it's not the only things I can think of. But basically, given the recent projects I've done, is the more natural results I can think of. But then, this is more related to quantum disordered systems. So quantum disordered system, this maybe talks to another class of people of the group. So obviously before I've done. So basically what I've showed you in part 2 is techniques that we borrowed from quantum spin glasses. Or that, the technique that we applied, they have been actually devised first with Subir Sachdev with the Heisenberg model of quantum magnetism, but there are also people like Thierry Jamarki who have worked on this kind of techniques. So I would say there is more a side of quantum disordered systems and related to many-body localization, because that's basically what I'm currently doing in LPTMS. And on the classical side, it's my expertise is more on the dynamics, and also I know also all the static approaches, standard approaches from classical, let's say, spin glasses. For example, what I showed you. What I showed you there. To compute this, what Pierfrancesco and collaborators did is to use techniques developed by Lenka Deborova, for example. So I mean, I know also the static way of doing things, but maybe I've focused more on dynamics.
Can I ask you a question
yes.
related to this? So you have those equations that you showed, but can you go back to the dynamic?
The dynamical equations?
Yeah.
This?
Exactly.
Okay.
So here, you were right. I think so. Here, this is equilibrium, right?
This is equilibrium.
This equilibrium I bring into time transition.
Yeah, time exactly.
And so I have two questions. So this kernel here, you say is a force correlator, but this potential. This potential, okay, depends on which potential
you can make.
You pick, but this might be a, let's say, multi-body average, right? It does not need to. It's not going to be a Gaussian correlator of the field H, right?
No, yeah. Okay. No, not at all.
So how do you deal with that? Because you mentioned numerics and you mentioned analytics. Can you?
Okay, so numerics.
Is it obvious to explain it? So
yeah, so there is no okay. So if you want to solve the prime for now, there is only I mean really the true time dependence of the prime. There is only numerics that has been done. There is if you want you can. There is maybe one example in which you can solve analytically those coupled equations is the if you take the limit of very small density, then you can actually this has been done by Francesco Zampo. So you can actually solve the equation, but apart from that, there is no fully analytical solution. What we did analytically was to focus on special regimes. So typically, what you can solve instead is for example, to get the transition or the way that you can make an ansatz basically for the dynamics at long times. So typically the dynamics at long times in a glassy state would be, for example, would be that you would have a plateau of these correlations plus some fluctuation that is small, and then you can solve the equations in this ansatz. Actually, I haven't talked about this, but there are many ansatz that comes from spin glasses that you could try maybe to enforce here, actually directly put this in the equations, see if it simplifies a bit. This hasn't been done actually. And so what all the analytic stuff that we have done was basically to put this kind of ansatz and describe the almost equilibrium behavior, or to focus close to this transition where you have a plateau here, so you can get, for example, the exponents of how you reach the plateau, and basically to compare with the curve. I mean, with the most standard theory that is called mode coupling theory for which is a different approximation for this kind of system. So it was to compare the bit between those two.
And instead, for what concerns the non-equilibrium dynamics,
yes. Sorry.
You didn't show any. So this equation would look a little bit more nasty, I guess.
So what you would have is that basic. Okay, so you give up obviously the t minus s here,
yes.
And so here you have fluctuation dissipation theorem, which means that you have a kernel that is the same here and there. But in the out of equilibrium dynamics, we would have still this kernel here, but you would have two others. So one would be the friction kernel, basically, and another one is basically the kind of spring, time-dependent spring that you have on your system or on your particles that are a bit confined by the interactions. So you have three kernels, and still, but what I say it's the same because it's still self-consistent. You have still a process for the gap, and three associated kernels that you have to, which are response and correlations of the system defined on the gaps.
And this mean square displacement would depend on both times.
The mean square displacement.
See aging and stuff like that.
Yeah, exactly. Yeah, actually, this. So you see those numerics here. So this is equilibrium, but actually Alessandro is doing also to see the aging processes and what is expected in this way. But for this, you have to solve numerically for three different kernels.
So the nodes that is used in the numerical simulation, because if you want, in the plot that you have.
Sorry.
Here, there.
This one?
Yeah. It's order 10 to minus 2.
It's order?
That you use to solve the numerical
Wait.
I mean, you discretize time.
Yeah, I think. Yeah, I think it's a. I don't think it's a fixed. It's a fixed. Right. I think at longer times they don't take a fixed. No, I think they go to the minimum possible at small times, and then you do a more complete space. Otherwise, I don't think you can reach many. No, I think so. I think so.
And another
Sure.
So imagine that you look at the perceptron thing that you showed. So
Yes.
when you are so if you take the
Phase diagram, yeah.
Yeah. Now imagine that you are at small alpha,
Mm-hmm.
but you are at sigma negative. So you are like
So here?
You are in this configuration.
Yeah.
Now, imagine that you do the quantum version. So what you are doing is that you are diagonalizing the free motion in a space where you have obstacles, which is a billiard.
So you have plane waves and you have
plane waves
berries.
plus obstacles, which
Yes.
is a billiard. And now it's a billiard with noise, so it will be chaotic,
Mm-hmm.
I have to say. Now imagine that you increase alpha. At some point you enter in this regime where you have a lot of
Yeah. Mm-hmm.
a lot of classes. What is your guess for the behavior of the system? So at low alpha is chaotic, I guess. So when you increase alpha, what happens?
Well, so okay, I don't know exactly, but what we thought is that what we thought is that okay, you have some obstacles. So in this kind of system, what you expect is that I mean, there are two things. What we thought about is that physically, truly in the system, if you would increase this, then maybe you would have more scattering, okay, between this, and then you could have some kind of Anderson-like transition in n dimension, okay. But this, I mean, this you cannot. I mean, this is a truly thermodynamic computation, so it's out of the range of this kind of computation, no. But I mean, physically, if you would do that. So below this, I mean below here, basically I guess at some point you would have some kind of, you have so many scattering that maybe you have, I mean it's expected that when you have disorder and if you increase the number of dimensions, you would have Anderson localization at finite disorder strength. The problem is that, well, we thought about this, but simulate, I mean Anderson localization in n dimension and large. Well, I don't think it's so. And this would be typically missed by such kind of phase diagram. You cannot write partition function. But so this is totally rated. I mean, so nobody has tried to do this kind of quantum billiard stuff. No. I guess in big n dimension it would be a bit hard. But there should be some localization transition, I guess.
Questions? No, I think we can
Okay, thank you.